Okay, I'm going to talk about Coulombs Law. So, hopefully my pen's going to work. There we go. Oh, I don't like that. There. All right, so last class we talked about Charles de Coulomb a little bit. Basically, came up with the relationship between the strength of charged objects and the attractive force between them. So what he was able to basically show was if we have two charged points, like say this guy and this one, and we charge them up with a specific amount of charge, I don't know, let's say 10 microcoulombs and say 12 microcoulombs. What we're basically saying here is that from their neutral state, we've added 10 microcoulombs of extra electrons into this one, and we've removed 12 from this one. So, this one has more electrons missing than this one has, so maybe the other 2 microcoulombs of electrons went off to some other object over here that we don't really care about. Okay, we're left with this situation. Now, would the force between these two objects be attractive or repulsive? Good. So in other words, this would experience an electric force of attraction to the right, and this to the left. Okay, what's really going on here behind the scenes, of course, is that you've got an electric field in between these two guys, and since each has an electric field and those fields are able to interact, okay, it's the interaction between those fields that provides that attractive force. Now, Coulomb looked at this not really probably directly as fields, but just as what that force is, and he was able to come up with the following relationships. Okay, the force is proportional to the charges that we have. Call that Q1 and Q2. All right, so as we increase these charges, that force increases directly proportionally to them. All right, so if you were to kind of like graph that relationship out, okay, you'd have a direct relationship. Okay, so double the amount of one of the charges and you get double the force. Double the amount of both charges and you get 4 times the force, and so on. All right, so it's a direct relationship between amount of charge measured in coulombs and the amount of attractive or repulsive force. If you switch this to being positive or switch this to being negative, you would now flip the arrows and these things would repel each other. Okay, everything else would remain the same mathematically, just the direction of attraction or repulsion would change. Now, as the distance increases, we know that fields weaken as we move away. All right, so the force will drop off, but it doesn't directly drop off. It's actually inversely proportional to the distance between them. Okay, so the distance between them is r. All right. So let's just draw the relationship, a similar graphic here. Okay, but now we want to relate the distance between the two charges to the amount of force between them. Okay, call that in meters, and units here is coulombs, and of course units here is newtons. So you get an inverse squared relationship, which is going to look something like that. Okay, so as you move away, all right, you get an exponential drop off in the amount of force between these two things. All right, the final form then of this law, when you kind of put it all together, looks like this. The electric force between 2 point charges is calculated as K Q Q over R squared, or sometimes Q1 and Q2. All right, this is a constant, and it's Coulomb's constant. So much like with the formula for gravitational attraction, which is GMM over r squared, you need a constant to put it in terms of newtons. Okay? These are the two charges measured in the units coulombs. We'll review what those are in just a second. Okay? And then this is the distance between the charges. So let's just look at this. This is like gravity, an inverse square law. And it doesn't hurt necessarily to take a quick look at where these inverse square laws come from if we haven't already done so. So we'll just do that in a second. Okay, so I just found a quick little graph here to kind of help explain what's going on. If you imagine that, let's say you have some charge here, right? Let's say it's positive. In 3 dimensions, you have your field lines pointing out of it, right? So in 3 dimensions, okay? Now we're going to imagine the density of field lines, right, in space around this object. And we're going to imagine, okay, at different r values as we move away, right? There's 1r, here's 2r, here's 3r. The surface area of the entire sphere that this passes through, right? So area of a sphere, how do you calculate the surface area of a sphere? Anybody remember? Is it not 4 pi r squared? Yeah, does that sound right? And so this is a constant, right? So the area of a sphere, besides the 4 and the pi, really is related to the square of the distance. So in other words, A is proportional to the square of r. So what that means then is that the area through which our field lines are going to pass or permeate, and therefore the density of field lines passing through this surface or shell, right, is going to change. So at 1r, our surface area is just 1. But at 2r, the same number of field lines are now passing through a shell area that is 4 units, right? 4 units of area. Okay, the reason being is because in this formula we've converted this to a 2. 2 squared is 4. By doubling radius, the area goes to 4. And then, of course, by tripling it, you now get to 9 and so on. So in other words, the density here, d equals 1. Here now is dropped to what? Well, it's 1/4, right? Here you have one group of field lines for one area. Here you still have one group of field lines. They're more spread out, but now for an area of 4. And here the field line density is now 1/9 of what it was as your area jumps. As your radius increases, the area through which those field lines pass increase at a squared distance. In other words, the strength of the field drops off at a squared distance. That's why you see these inverse square laws kind of pop up all over the place. It happens with brightness, it happens with the loudness of sound, it happens with magnetic fields, it happens with electric fields, it happens with gravitational fields. It's all based on this kind of geometrical idea. It's not magic, it doesn't come out of nowhere. It's sort of a logical extension of the way that point sources of either gravity or electricity or brightness or whatever extend out into space. So why don't we try just a quick little intuitive problem here before we get into actually crunching numbers with this. So here's the proof that Coulomb basically made. And we'll just actually do this even without the whole K value. He said this, Q1, Q2 over R squared. Okay. Let's say that in situation 1, we have a charge of 1 microcoulomb, let's say. And here we have a charge of 1 microcoulomb. And let's say that this is 1 meter away. Okay, let's just say. Actually, sorry, I don't even want to put numbers here. let's say the distance is 1 meter, and we just have Q1 and Q2. Okay, and let's say we have a force of attraction of 1 Newton. Okay, well, what if we triple Q1, have Q2, and have R? What would FE be? All right, so let's look at the thinking on one like this. Actually, you don't even really need a distance either, right? Because it's totally intuitive. You can do without numbers. If you're just told that your initial conditions, right, are like this, and you got a 1 Newton force here, okay, well, let's look at what you're doing. You can consider this then to be your starting point. So we just call all these values 1, right? So in the first situation, you get 1 Newton. Now what you're doing here is you're saying you're going to triple Q1. So 3 times Q1, okay, multiplied by half of Q2. All right, well, what that's going to do on the top is it's going to change the top to 1.5 what it was before. Okay, since we just considered the top 1 times 1, well, 3 times a half gives you 1.5 on top. On the bottom now we have this, so we've gone 1/2, but remember that it's a squared 1/2. So we end up with then, what's the square of a half? A quarter. So 1.5 divided by a quarter is like 1.5 divided by a quarter. And there should be, right, 2 quarters per half. So you should end up then with, since you have 3 halves, you should end up with 6. Okay, so 6 times more than what you had before, right? So you triple this, you have this, so the tripling brings it up 3 times. The halving brings it down to a half, so 3 times that's a 1.5. If that's all we did, we'd end up with 1.5. We've also brought them much closer together, and since that bringing together acts on a square rule, okay, we got to square the bottom. So we got 1.5 divided by a quarter, and we end up with 6. So we could say then, by doing those changes, we end up with 6 times this, which is equal to 6 newtons. So without any numbers put in, okay, we can just intuitively sort of figure out what's going to happen. I don't know if that's really intuition, but sort of a numberless way of relating those things, okay? A lot of these kind of older physics guys, that's the kind of relationships they were doing. All right, so now we got to talk about the actual units so that we can write this out in terms of newtons. First things first, what is a Coulomb? Well, it's an amount of charge. Okay, and actually it's a lot of charge. So it is the amount of charge equal to 6.2 times 10 to the 18 elementary charges. All right. So E, that is the charge on 1 electron or 1 proton. For the electron, we call it a negative charge, and for the proton, we call it a positive charge. The symbol E is the symbol for the elementary charge. So if we gather together 6.2 times 10 E's, we have an amount of charge equal to 1 Coulomb of charge. Okay? It's kind of a similar idea to the mole. It's not the mole, but it's a similar idea to the mole. You need a certain number of particles to make up a mole. You need a certain number of charges to make up a Coulomb. So what that also means then is that we could figure out what the charge on E is. The charge on a single E then would be this. And you get a really small value of 1.6 roughly times 10 to the negative 19 coulombs. So we could then say in terms of coulombs, this is the charge on a single electron or proton. Symbols wise, E with a negative sign is the symbol for an electron. And for a proton, it's just P. I don't know who comes up with these things, but there it is. There's actually something called a positron. It gets E+. I think that's probably to do with the nature of the particles. The particles are not the same in the same class. Okay, this is made up of quarks, whereas this is like truly an elementary particle. Don't know if that really matters to you, but a positron is simply a positive electron. Luckily, we don't have to worry about that too much, but just in terms of symbols, there is an E+. Do not put E+ for proton. That would be incorrect. Okay. So because a Coulomb is such a gigantic amount of charge, in our daily lives, we generally deal with microcoulomb charges. Like a lightning strike might travel 1.5-ish coulombs of charge, give or take. So you can imagine a lightning strike is quite a, impressive display. Lightning might transfer. Okay. If you get a static shock, you might be passing around a microcoulomb of charge, so a millionth of a coulomb. Maybe a bit more. Maybe like tens of microcoulombs, but still like a fraction of a coulomb because a coulomb is so huge. So just a little side note here, coulombs are defined units. In other words, they're not considered fundamental units in SI. So you can remember in SI that the fundamental units that we're used to using are meters, kilograms, seconds, Kelvin, mole, candela, and of course, amp. Okay, so the definition of a Coulomb actually it is the amount of charge delivered in 1 second by a 1 amp current. We'll get more into currents later on. So the Coulomb then is 1 amp second in fundamental units. Okay, and 1 amp therefore is equal to 1 Coulomb every second. This is generally how you learn about amps. You talk about coulombs first, and you say that a 1 amp current is 1 Coulomb per second, a 2 amp current is 2 coulombs per second, and so on and so forth. But it's actually the amp that's fundamental. This is defined using, I believe it's the attraction between two 1 meter long wires with current traveling in opposite directions and measuring the attractive force between them. We'll look at that later. I could be wrong on that, but it's got something to do with that kind of a relationship. Is K. So K, which is Coulomb's constant, sort of like G, right? G is Newton's constant. We need to do Coulomb's constant. So Coulomb's constant is 9 times 10 to the 9. Now, what units is it in? So to figure that out, we need to look at Coulomb's equation here, Coulomb's law. And figure out how we get to what the units are here. So first things first, we know that's coulombs we know that's coulombs. And since we're in MKS units, we know that that's meters, right? And we know that we need to have newtons over here. So coulombs and meters, well, neither of those contain newtons. So we know first off, the unit here must contain newtons, okay? So it's got to leave you in newtons, and it's got to cancel off double coulombs. So we'll put it to coulombs -2, okay? And then it's going to be divided out by square meters. So it's got to have meters squared. So basically, you have this. However, this is not in base units. It's not in base units. So we have to actually convert it out to base units. If we look at that, newtons, Coulomb -2, meters squared. This is the most kind of logical way to write it, but it wouldn't be like fully correct. Let's see here. So newtons are kilogram meter per second squared, right? Coulombs are amp seconds, so amp -2, second -2, and meters squared. So now we're going to go through and collect up all our units. Let's see here. So we've got kilograms. We've got meters cubed, it looks like. We've got amps -2 and seconds -4, I think. I'm going to double check on that. Well, anyway, I've actually just noticed that it's written like that most of the time, but I'm pretty sure this is what it breaks down to. I have to do some digging just to make sure. To be quite honest, just leaving it like this is the most sensible. So let's use it to solve a problem. A negative charge of, I'm going to say 10 microcoulombs is placed to the left of a 12 microcoulomb positive charge. Calculate on each charged object. Oh, I'm going to tell you how far. Let's say 5 centimeters. Okay, so we'll draw that really quick. So we've got a 12 microcoulomb charge here, and next to it we've put a 10 microcoulomb charge. And we've placed them 5 centimeters apart. All right, so before you get into solving this, make sure that you are converting this correctly into full coulombs, okay? And that you're converting this into meters. So this is 10 times 10 to the -6 coulombs. This is 12 times 10 to the -6 coulombs. Or you could call it 1 times 10 to the -5 and 1.2 times 10 to the -5. And this is 5 times 10 to the -2 meters, okay? And you just go ahead and you solve it. Also make note of how much larger Coulomb's constant is than newtons, all right? Gravity is much weaker. You need much larger masses than you need charges as measured in kilograms versus coulombs in order to get forces on the same magnitude, okay? and then you just solve it. So we're getting 432 for that. Okay, and I think that's probably where we'll stop today.